So Pythagorean theorem was discovered several thousand, 2,000 years ago. This is in section 5.8 of our textbook, and it's about right triangles. And if you have a square angle, that's called a right angle. Square angle. And if you think about measuring angles in degrees, then either way it measures 90 degrees or a quarter of the way around a full revolution. So as long as you have a right triangle. What they discovered years ago is that if you take the sides that come off of the right angle, so that side there and that side there, those are called the legs. So we have a leg called A and we have another leg called B. And if you measure them, so I measure A, let's say I measure A and it comes out to be A equals 1. And I measure B and B comes out to be 1, 2. Now, I know in that picture that's not quite right, but we're going to go with it. Pythagorean theorem says there's this relationship between the three sides. So you measure one leg, write it down, square it. You measure the other leg, write it down and square it, and then you add those two together. Pythagorean theorem says that sum of those squares is always going to be the same as the square of the long side. So I'm just going to call that C, because I didn't measure that. But this is what the Pythagorean theorem says. If you take the legs, A and B, and you square them and then add them up, you'll always get the length of the long side. And the long side is called the hypotenuse. The reason the hypotenuse is always the long side is the total amount of degrees for angle you can have inside of a triangle is 180 degrees inside. The right angle took up 90 degrees. So that means the other two angles have to share the other 90 degrees to get a full 180 inside. So since those two angles are smaller, that means these two sides have to be smaller than this one, because they're opposite those angles. Okay, so one important thing is just recognizing the difference between the legs that come off the right angle and the side opposite the right angle, which is the hypotenuse, because that's the order that they fit into the equation here. Let's follow that a little further. 1 squared is 1. 1 squared is 1. 1 plus 1 is 2. So what that tells me is that the square of the long side, meaning there's some number that I can multiply by itself and get 2. From the previous chapter, we learned that if you can square some number and get an answer, reversing that is the square root. So from the previous chapter, we know if c squared is equal to something like 2, then c has to be equal to the square root of 2. So what? Well, it gives us the ability to, if I don't know what that length should be, like for example, in construction, I use this sometimes to make sure I'm measuring things right. Or I'll measure a couple of things, then I'll calculate to see if that distance is the one it should be. Like, for example, I want my walls to be at right angles to each other. I don't want it tilting in, I don't want it tilting out. So taking measurements like this can help me assure that I have my walls to the floor at a right angle. Right? So when I built my house, I used this a lot to check things like that. Here's the crazy thing, though. Thousands of years ago, when people discovered this, they believed the world was rational, which meant you could describe the world with whole numbers and fractions. Problem: this number cannot be written as a fraction. It's difficult to calculate. Years ago, like when my mom was in school, they used a thing called the slide rule to calculate it. And then later we have calculators. And so you have to use a calculator if you want to say, what is the square root about? So I got to go over to my calculator next. I'm going to use Desmos. And so then I click the square root button, and then I type the number that goes inside the box, 2. So my calculator says that the square root of 2 is about 1.414213562. And it turns out that decimal goes on forever and never repeats. Just kind of bizarre. There's no pattern to it. What do I mean by pattern? Well, if you take something like 1/11, that has a repeating pattern. It's always 909090, and then the calculator rounded the next 0 to a 1 because a 9 came next. So again, my point is the only way to state a square root that's not perfect exactly is to write it as a square root. So sometimes the book and the problems will say, find an exact answer. The only exact answer for this length right there is the square root of 2 written as the square root of 2. Once you plug it into a calculator, you have to round. So if I plug this into a calculator, that means I have to round it. And so I'm going to put a wavy in equal sign to indicate I rounded. So equals is exact. A wavy equals means approximate that I rounded. And to 2 decimal places, the nearest hundredth, it's about 1.41. So if I was measuring in centimeters, then this would be about 1.41 centimeters. Is it exactly 1.41 centimeters? No, there's a little error there that I didn't include. So if the problem says state an exact answer, you don't type this into your calculator, you just write that right there. If it says approximate to the nearest hundredth, then you plug it into your calculator and then you write that as the answer. Okay, so let's try a couple from the book exercises. All right, so let's look at number 3. Add to page, please. So this is from the homework problems in our section 5.8 of this book. All right, so the lengths of the 2 legs are 12 and 16 meters. Find the length, the exact length of the hypotenuse. So once I see exact, that means I don't need to use my calculator at the end. So then I like to draw it just to keep myself straight. There's a right angle. One side is a little longer than the other. So I'm going to say this one is 16 and that one is 12. It doesn't matter if you do 12 then 16 for these, as long as the legs are attached to the right angle. And then they say find the hypotenuse, which is going to be this long side, which I'm going to call C. So Pythagorean theorem says a squared, one of the legs squared, plus b squared, the other leg squared, has to equal c squared. And so plugging in, I'm going to say this one right here is my a. So I'm going to get a 16 squared. That means this one right here has to be my b. That's going to be a 12 squared. Equals, I don't know what c is yet, so I'm just going to say c squared. I'm trying to find c here. All right, 16 times 16. Oh, I don't remember that. Let's calculate it. Or again, you could whip out your calculator for that if you wanted to. 6 times 6 is 36. Times 1 is 6, 7, 8, 9. 0, 1 times 6, 1 times 1, 6, 9, and 6 is 15. All right, so this one's 256. I remember 12 squared is 144. So next I have to add those up. So underneath here, I'll add 144. 6 and 4 is 10, carry the 1. 5, 6, 7, 8, 9, another 10, that's nice. 1, 2, 3, 4. Oh, exactly 400. All right, so c squared is equal to 400. And then from the previous section, we know that if something squared is equal to a number, that means that thing that we squared has to be the square root of that other number. Okay. Now, I could stop there, but I'm thinking here, wait a minute. 4, the square root of 4 is 2, because 2 times 2 is 4. And the square root of 100, well, 10 times 10 is 100, so that would be 10. So I think this actually has an answer that's not a crazy decimal. So I'm just going to go to my calculator and double check that. Calculator. So hit the square root button first on most calculators, and then inside the box, say, what do you want the square root of? So this says 20 times 20 is 400. So actually, I can use my calculator to finish this and get an exact answer because there's no crazy decimal. So a better answer here than the square root of 400 would be to say the answer is just 20. And that's my exact answer. I didn't have to round. With the previous problem, I had to round, so that second answer I wrote wouldn't be exact. Questions? Try another? Yeah. Let's look at number 7. This is again a problem from section 5.8 of our book. The lengths of the two legs are 2 and 21. Okay, so this is a skinny triangle. So I'm going to say that's about 2, and maybe that's about 21. And I'm not worried about getting it exact, but it's shaped something like this. And there's a right angle between the legs. And they want me to find the hypotenuse, which we usually call C. So like before, I have to plug in a squared plus b squared equals c squared. A is 2. B is 21. 2 squared, I've got that. 21, I'm going to ask my calculator about 21, but I could do it myself. But my calculator's sitting. 21 times 21 is 441. All right, so plus 441, that would be 445. Okay, so I'm looking for a number whose square is 445. So that means the number I want has to be the square root of 445. All right, now 445 isn't ringing any bells as a nice number that was multiplied by itself. So I'm going to check with my calculator to see if it is a nice square root. Sure. Square root of 445 is 21.095023111, right? There's no pattern going on there, which means the calculator probably rounded. So that's not the exact answer. So again, if you plug a square root in a calculator and you get a decimal that doesn't seem to have a perceivable pattern to it, like 1/11th is 090909, this doesn't have something like that. The only exact way to write the answer is like that. This answer over here is actually approximate because the calculator probably rounded. So since this problem said find the exact length, I'm just going to stop here and say, I believe that's the length of the hypotenuse exactly. If it said round to the nearest hundredth, then I'm going to use the calculator version. And there's the last couple ask for that. Better? Yeah, let's do one more. Let's try number, was 9 in the homework? I don't remember. Yeah, it was good. 9's a good one to try. Add to page, yes, please. Thank you. I thank my computer often, but I read online that you're not supposed to thank AI because that makes it think about your response and uses energy it didn't need to use otherwise. But after watching that Avengers, what was that? The robots that tried to take over the world, they were AI. I'm thinking I should just be nice and thank AI. Okay, back to reality. So the length of one leg is 12. The length of the hypotenuse is 19. Okay, so this one's a little bit different. All right, so let's say this is my 12. And then the hypotenuse is 19. So maybe that could be around 19-ish. So that would be my 19. And I don't know this other leg. So I'm going to color that one different. And I'm going to put the right angle there. So I have a leg. Let's say this leg is going to be A. I have the hypotenuse, which we always should call C. And I don't know the length of the other leg. So I got to be a little more careful on this one because I wasn't given the two legs. I've got one leg is 12. The hypotenuse is 19. Okay, so do you have to draw a picture? No, but it helps me get things right. So I think that's the right picture. And then I want to plug that into a squared plus b squared equals c squared. Okay, so this time I'm going to have a is 12. I don't know b, so I'm just going to leave it as b squared. And oops, I forgot my square there, sorry. And the c is 19, so I'm going to put a 19 squared over there. All right, let's see. Well, I guess I need to square the 12 and square the 19. So the 12 I got, that's 144. I don't know the square of 19, so either I need to write it off to the side or whip out my calculator. Down this time. 9 times 9 is 81. 9 and 8 is 17. 1 times 9, 1 times 1. 1. 9 and 7 is 16. All right, so I'm getting 361 for that one. Now we've kind of done things like this before where we have some variable that we're trying to find and there's stuff around it. And what we ended up doing pretty much all the time is if that variable was connected with something like a plus there, then we would subtract this other number to get the variable alone. So I think I need to subtract 144. I'm going to try it and see what happens. See, if I do that, on the left side, I'll have 144 minus 144, which is 0, plus b squared. Well, 0 plus anything is itself. So yeah, I cleaned it up. So now there's just a b squared on the left side. The other side, I got to do that subtraction. I'm going to write it off to the side, or feel free to whip out your calculator at this point. When we're working with roots in the Pythagorean theorem, we pretty much have to use a calculator for the end part at least. I'm going to borrow here. 11 minus 4, 7. 5 minus 4, 3 minus 1. Okay, I'm getting the other side is 217. That's not very nice. Okay. Okay, so we think the square of b is 217. So that tells us that b should be the square root of 217. All right, I don't recognize 217 as the square of a number I know, like 144 I recognize as 12 times 12. So the next thing I should do is ask my calculator to see if that can be simplified but not rounded, because it wants an exact answer here. So then I go to my calculator and check, am I done or not? Desmos, what do you think? Square root 217. And again, I am pretty much reliant on my calculator for this. All right, so the calculator says 14.73091986. Do we see a pattern in that decimal that repeats? The answer is no. So that means that's a rounded answer, not an approximate answer. So I don't need to write that down because the problem said, give me the exact answer. The calculator answer doesn't seem to be exact, so I would stop here and say, I'm pretty sure that's the exact length of this other side. Now, I could have screwed this up. I just want to think a little further. I am going to look back at the calculator answer for a minute because I want to see if it makes sense in this picture. 14.7 around. So if I was relatively accurate in saying that's 12, and that's about 19, that looks like a little too long. Does it seem reasonable that this could be about 14.7? Well, it has to be longer. Well, it doesn't have to be, but it's longer than 12, which I guess is okay. It has to be shorter than 19. Could be right. Again, I could whip out a ruler and measure it out. Actually, I do have a ruler right here. Let me try. Let's see if that's 12. 19 is what, 5 farther? No, 7 farther. So that would be around maybe that long. Okay, my picture's a little off. Okay, so if I call this 12 there, then I think 19 is going to be more like that. 12 versus 19. 12 and another 7. Yeah, it's not bad. This side is definitely longer than 12 and shorter than 19. So to say it's about 14.7 seems reasonable. Right? If I calculated something like 147, no way that could be 147. If I calculated something like 2, there's no way that could be 2. Right? So I can kind of guess to see if this answer over here is in the range of a reasonable thing in this sketch. So that's another reason I draw the picture. And sometimes redraw it, trying to be a little more accurate with a ruler. All right. That was fun.